What if I told you that every single skyscraper, every bridge, and every home you see is held up by a mathematical secret buried in the dirt, and that the man who discovered it didn't even start as a civil engineer? This is the story of the most important number in construction, the ultimate bearing capacity, and the deceptively simple equation that determines it. Our story doesn't begin at a construction site, but in a physics lab in 1921. A scientist named Ludwig Prandtl was studying how hard metal shapes punch into softer materials like clay. But one brilliant mind saw a parallel to a much bigger problem. Carl Terzaghi, now known as the father of soil mechanics, realized that a foundation pressing into the earth was just a larger-scale version of Prandtl's sponge. He took that seed of an idea and grew it into the first reliable theory to answer the fundamental question: how much load can this ground actually hold? But to build a universal theory, he first had to make some critical simplifications about how the real world behaves. Terzaghi's model is built on three main assumptions for what we call a shallow foundation. First, he assumed the foundation is shallow, meaning its depth is less than or equal to its width. Second, he modeled it as a continuous strip footing, like a long, unbroken concrete wall under a building. This simplifies the 3D problem into a 2D slice we can analyze. Third, and most crucially, he assumed the soil would fail in a general shear failure. This isn't a gentle settlement. It's a catastrophic, well-defined rupture, where a clear wedge of soil is pushed downward and sideways. But to predict when that failure happens, he had to account for every ounce of strength the soil could muster to fight back. And that fight happens in three distinct zones: the soil's battle plan, the three failure zones under a failing footing. The soil doesn't give up uniformly. Terzaghi's model divides it into three distinct battle zones. Right under the footing is Zone I, a triangular wedge that moves down as one rigid block. Below that, Zone 2 consists of radial shear zones, curved areas where the soil is shearing and flowing. And out to the sides is Zone 3, where the soil gets pushed upwards in a state of passive resistance. Think of it like this: Zone 1 is a giant foot stomping down, and Zone 3 is the surrounding soil bracing its shoulders to stop it. The key to the entire calculation lies in quantifying the heroic resistance generated in this passive zone. How do we calculate that passive resistance? The best analogy is a retaining wall. In soil mechanics, if a wall moves away from the soil, the pressure drops, that's active pressure. But if you push the wall into the soil pushes back with immense force, that's passive pressure. Our failing soil wedge in Zone I acts exactly like a wall being shoved into the passive Zone 3. So, we can use established physics for passive earth pressure. But that's only one of three defensive forces. The soil also fights back with its cohesion, its innate stickiness that holds particles together, and with the surcharge effect, which is the weight of the soil column already sitting to the sides of the footing. Now, with our three defenders identified: passive pressure, cohesion, and surcharge, we're ready for the ultimate balance of power. It all comes down to a vertical force equilibrium. On one side of the scale, the downward forces, the structural load Q, and the weight of the soil wedge itself. On the other side, the upward resisting forces. Our three heroes from the passive zone. By applying geometry and trigonometry to that wedge, we can express each force in terms of the footing width, B, soil weight, cohesion, C, surcharge, Q, and the soil's internal friction angle. When we group all the terms related to cohesion together, they form a factor we call NC. Group the surcharge terms, that's NQ, and group the terms related to the soil's unit, weight, and the footing width. That's N. These are Terzaghi's legendary bearing capacity factors, NC, NQ, and N. They are not arbitrary constants. Each is a direct mathematical function of the soil's friction angle. Their values, often looked up in a table, condense an immense amount of geometric and physical complexity into three simple numbers. Plug them into the equation, and you have your answer: the ultimate pressure the soil can withstand before general shear failure. This was the groundbreaking formula that gave engineers their first true predictive power. But the real world, of course, is never as perfect as a theory's assumptions. Terzaghi gave us the cornerstone, but later scientists built the rest of the house. His original equation was for a long strip. What about square or circular footings? Researchers like Meyerhoff introduced shape factors. What if the soil fails in a softer, local shear mode? Modification factors were added. And what about the water table? This is critical. Water changes the effect of stress in the soil, and its presence must be accounted for in the term, which is a topic for a deep dive all on its own. The Terzaghi equation is your starting point, the fundamental law. Every other formula in your codebook is a refinement of this brilliant original idea. Conclusion. So, the next time you walk past a massive structure, remember the hidden calculation happening below. It's a balance of forces, derived from a century-old punch test, that keeps it standing tall. Quote. Number 2. The true foundation of engineering isn't concrete. It's the ability to model chaos with elegant math. If this deep dive into the bedrock of geotech helped you, show some love, smash that like button for wins of thought. It truly helps us make more content like this. Your turn. What is the most challenging soil condition you've ever encountered on a project? Was it soft clay, loose sand, or something else? Drop your stories in the comments below. And to make sure you don't miss our next video, where we'll unravel the tricky effects of the groundwater table on bearing capacity, hit subscribe and ring the notification bell. Thanks for watching, and we'll see you in the next one.